Every year, we receive dozens of requests from professionals around the country to participate in Geography 2050 by presenting lightning talks. As I said yesterday, they range from graduate students to CEOs and everything in between. The one thing they have in common is they are passionate about their topics, and these presentations are often among the best you will see. This afternoon, we're going to have 2 sessions devoted to lightning talks, and this is the first group that has been organized by AGS Counselor and Deputy Director at the State Department, Dr. Wes Reisser. Wes?
Good afternoon. I can't hear you. It's dark. You've eaten lunch. Good afternoon. Let's wake up a little bit here. We've got some high energy ahead of us now with this next set of lightning talks. So without further ado, we will get rolling with these. So first up, we have Dr. Mattia Amadio from the World Bank, the Risk Data Literacy Standard, opening up risk information for better risk management.
Good afternoon, fellow geographers. My name is Mattia Amadio. I'm a disaster and climate risk consultant for the World Bank GFDRR. And today I'm going to introduce you to our latest project, which is called the Risk Data Library. GFDRR stands for Global Facility for Disaster Risk Reduction and Recovery. It's a global partnership program established in 2006, led by the World Bank and other important institutions to support developing countries on disaster risk reduction and climate change adaptation. One of the main objectives of GFDRR is to support disaster risk information, and since 2015, the Sendai framework for disaster risk reduction made clear that the first priority to become able to reduce disaster risk is to actually understand it in all its dimension and complexity. Since then, the demand for detailed and updated spatial data set representing the component of risk has seen progressive increase. However, there are several challenges remaining. Risk data can be hard to find, to access, and to be fully understood. And more often than not, it's not accompanied by proper and complete metadata describing it. And metadata ensure that the data are fair, an acronym that stands for findable, accessible, interoperable, and reusable. The Risk Data Library addresses these issues by providing standards and tools covering the main components of risk as formalized by the most recent UN DRR and IPCC framework. Each component has its own peculiarity and thus needs specific attributes to properly describe it. We are going to quickly present each one of the 4 main components and the way that the RDL builds a schema of metadata attributes to describe those distinct elements. So starting with the hazard component, such as earthquake maps or flood maps, we need metadata able to describe both observed events and probabilistic modeling of magnitude and frequency, such as return period scenarios. And these scenarios can cover one or more hazard types, specific hazard process and triggers, such as an earthquake triggering a tsunami or flood triggering landslide, each one characterized by different intensity measure and uncertainty. Exposure data, on the other side, describe the risk receptors, which are physical elements and assets prone to suffer an impact from hazard events. These are characterized by categories such as population, built up and land cover, and specific taxonomies such as building a number of stories, etc. The vulnerability component can include both impact models, such as fragility curves and damage functions, and spatial socioeconomic indicators, such as wealth indices, age dependency, access to service, and it's characterized by applicability to specific hazard types and exposure categories. Finally, the loss or risk data is the one that links these 3 components together into specific calculation approaches, such as exceedance probability curves, which is then characterized by applicability to specific hazards and categories of exposure. The RDL has been developed and continues to be developed with the support of firms and institutions experts in risk analytics, which are also early adopters of the standard. The documentation, the RDL environment is made of several resources accessible to the public, the official website, Nexus, and the documentation repository of open standard and collection of existing risk data hosted by the World Bank data catalog. The documentation included the full reference to each element of the schema, examples and tools for metadata production. The current workflow for metadata creation, it's a work in progress and starts from a simple spreadsheet of data, then allowing to convert it into a standard JSON schema by using an online tool, and we are looking to make this even more friendly with a wizard once the standard is finalized. The risk data library schema is designed to be integrated into multiple data catalogs. In fact, we aim to build a constellation of risk data made out of contribution from multiple firms, organizations, academic authors, and general users of risk data. And finally, the Risk Data Library runs a fellowship program founded by the Swiss Re Foundation, which supports a community of risk data experts from 6 countries, some of them presenting here yesterday or today. Their objective across the program is to learn, create, and share disaster risk knowledge for their own countries or cities, ultimately adopting the Risk Data Library standard to make this data fair. So please have a look at the online material we have released, and don't hesitate to contact us if you want to become an early adopter of the Risk Data Library standard. Thank you.
Thank you. Next to the stage, we welcome Mr. Mohammad Fadli from the World Bank as well. Climate change vulnerability profiles and local adaptation strategies in Indonesia.
Good evening, ladies and gentlemen. My name is Fadli. I'm from Indonesia. I'm a Climate and Disaster Risk Data Fellow at the GFDRR. My ongoing project involves developing a climate change vulnerability profile and local adaptation strategies in Indonesia. So Indonesia is an archipelagic nation in Southeast Asia, comprising more than 16,000 islands, 99,000 kilometers of coastline, over 600 ethnicities, and more than 1,000 native languages. Geographically, Indonesia is situated in the Pacific Ring of Fire, which is exposed to geological hazards such as earthquake, tsunami, and volcanic eruptions. And influenced by the unique climate system, Indonesia is also exposed to hydrometeorological hazards, which are predicted to increase in the future due to the climate change. So the climate variability is spatially varied within the region, and the microclimates due to contour variations also play a significant role. So it is common that on the same day, one district suffers from flood, while others experience drought or forest fire. So for this reason, we have downscaled the climate projections to a resolution to 5 kilometers to get a good analysis of each landscape. This resolution is needed to cover different landscapes, including watershed or an island's areas. So since 2014, our national government has developed a long-term plan to cope with the climate change, including the latest climate resilience development policy, and this has been mainstreamed into our national medium-term development plan. We conduct sectorial prioritization, which includes marine and coastal, water, agriculture, and health sectors led by the relevant ministries and agencies. And the Ministry of Environment and Forestry has led the community-level program for climate adaptation and mitigation. Nationwide, it is targeted to be implemented within 20,000 locations by 2024. With this pressure to meet this target, we developed a tool to map vulnerability profile with the aim of narrowing down adaptation solution for each village in Indonesia. As the smallest unit of government administration, Indonesia has more than 83,000 villages, including urban and rural, that are spread across the archipelagic nations. As we know that climate risk is a function of hazard, exposure, and vulnerability, we combine the existing and future climate data with the village-level statistic data for all entire villages that we get from the Bureau of Statistics. So each village possesses various characteristics, including temperature and precipitation as a hazard, population density as an exposure, land cover change as sensitivity, and basic infrastructure as an adaptive capacity, for example. So we combining the historical, present, and projected climate data with the landscape information, we can derive the climate and hydrometeorological hazard for each of the village. Then, using a simple machine learning logic, we perform a separate cluster analysis within 6 subregions. Village-level data shows the multiple dimension of vulnerability. And the result is we have a sufferer cluster per regions as seen on the dashboard. The color coding represents different clusters categorization per region. So with the results of this clustering, we did not look for which village were the most vulnerable, because it has been done by another programs. But here we intend to matchmaking the list of adaptations based on the relevant characteristic of the village. So this methodology and tools are still being developed. We will add more parameters and more detailed data so we can provide more precise recommendations. And our goal is to build the resilience big data for Indonesia. And by the end of the project, we will place all the data into the World Bank data catalog and applied risk data library standards to consolidate a climate and disaster risk related data into one platform. So thank you very much. Please visit our beta version of the dashboard and to see more further information. Thank you.
Thank you. Next, we welcome to the stage Dr. Kevin Heaney of Applied Ocean Sciences, developing effective mitigation strategies for environmental soundscape changes in a rapidly melting Arctic.
Thank you. It's a pleasure to be here at Geo 2050. It's my first AGS meeting, and it's been tons of fun. We're going to do a deep dive here into a particular problem to address shipping noise in the Arctic. And we're trying to inform policymakers and international organizations on how they can make decisions. Here's a spillhouse projection, my favorite, of a shipping noise model that we've generated at AOS. You can see wind in the Southern Ocean near Antarctica and ships through most of the North Atlantic. This is the rotating globe of, again, what we're doing is we're modeling where ships are, we're doing the propagation physics in the ocean, and there's oceanography. The question we want to take this technology to is to address what's going to happen in the Arctic in 2030 and 2050 when the ice really recedes significantly. And there will be more ships, there will be different soundscape environments for the marine mammals that live there and the people who live off of that ecosystem. So you can see that the ocean's a complicated place and sound travels, well, I'll skip over that. we do know, it's, you know, the figure on the left is the measured ice extent of the ocean and of the Arctic Ocean, and it's dropping dramatically, and this will have profound impacts on the ocean acoustics. The two figures on the left are acoustic propagation in the central oceans, in the Pacific, and the ones on the right are for the Arctic. And so the Arctic is a different environment. Sound travels much better there, which is evidenced by the evolutionary development of acoustics for the marine mammals that live there. So working with PAIM and the Arctic Council and the World Wildlife Fund, we're looking at how do we assess the impact of sound pollution on the marine mammals that are living there, and where acoustics is central to their communication and environmental sampling. One of the products of this report were soundscape maps. The left is the winter map, and the right is the summer. You can see shipping noise dramatically increases as the ice recedes in the summer. And so this is a plot of a model based on 7 years of shipping data, and one of the things, the main thing you take away from this is over the 7 years from 2013 to 2019, multiple regions in the Arctic got significantly louder. Numbers here are like 10 or 12 dB, which is doubling and doubling and doubling and doubling. So the new study is to say, what do we do about 2030? And now it gets hard because we have to do economics. Where are the ships going to be, and how do we fold that in? What's the ice going to be like? Climate studies, propagation physics, biology, and economics get folded together. So we put together shipping scenarios to say, where will the ships be and what will they be doing? And that's a really difficult thing to do. This was before the Ukraine war, and you know, the economy of the Northern Hemisphere changed. So we have multiple scenarios. Plot on the left is a shipping model, and we're looking at 3 regions of sensitivity for marine life. And one is the Barents Sea, the Beaufort Sea, and then the Baffin Bay area. And so this is our first sort of result, which is going towards the World Wildlife Fund will present this at the Arctic Council, looking at the increases in noise and behavior of shipping in the Arctic and how that will impact the ecosystem there. And so our conclusions are too long for a lightning talk, and so we'll just say that it's a phenomenal program in the context that we need biologists, we need physicists, we need economists, and then we need policy people to say, how do we get something like this forward and actionable on an international stage? So thank you for your time.
Thank you. Next to the stage, we welcome Mr. Tobin McGilligan of CARTO, using geospatial analytics to boost climate resilience in Hawaii.
Hi, everyone. My name is Tobin McGilligan, and in the next 5 minutes, I want to share how the Hawaii Department of Transportation is using cloud-native geospatial analytics to boost climate resilience in Hawaii. What do I mean by boosting climate resilience? Well, it's some of the questions here on this slide. Transportation planning. Which roadway will wash out first in a bad storm? Where will groundwater inundation risks threaten infrastructure in the coming decade? Where will systems and services struggle to meet demand under accelerating climate extremes? What is the optimal placement and deployment of resources in order to prepare for the next emergency? Where is this boost coming from? Big data. Geospatial data today is being produced on a massive scale, and it's getting bigger every day. Terabytes and terabytes of information per second. How is this boost coming to us exactly? Only a cloud-based approach can handle it. The cloud automatically scales and distributes data storage and computing resources to effectively drink from the data fire hose. How are we harnessing this boost? We need geospatial platforms that are cloud native. Transportation planners at HDOT are using these platforms to answer questions like the ones I described. This is a sampling of some of the dozens of data sets that have been pulled together for Hawaii's climate resilience platform. Many of these exhibit the three characteristics of big data: volume, velocity, and variety. HDOT planners can filter, normalize, compare, and synthesize any combination of these inputs in order to capture the performance measure or extract the insight that they need in the moment that they access the platform. This is done simply by selecting a topic and a number of variables from a set of menus. Here I am selecting several climate data sets, for example. The priority of each of these variables relative to one another can be adjusted using the sliding value selectors. And the result is automatically updated in the map. This is powerful because it effectively enables rapid prototyping of analytical methodologies based on different assumptions or changing criteria or changing data sources. This is also powerful because it allows us to move beyond visual inference. Imagine how challenging it would be to visualize 50+ data sets all together in the same map. You couldn't do it. There simply aren't enough symbols, textures, space on the color spectrum to get our minds to differentiate 50 different data layers. And so this approach is combined with parameterized composite scoring functions in order to distill all of these data layers into a single number. Under the hood, this is facilitated by the H3 hierarchical geospatial indexing system. That's the hexagons that you keep seeing in every screenshot. This is perfect for cloud computing because the topological relationships between grid cells are predefined, which means we can handle calculations at the volume, velocity, and variety required for geospatial data. Say I want to add a dimension of equity to my analysis. I can navigate to median household income just as one way to measure that, and by adjusting the slider, I can pinpoint where investment would impact low-income households the most. Let me add in what I know about storm surge on the Big Island of Hawaii. Panning over there, I can maximize that value selector in order to incorporate more and more of my storm surge conclusions into my index composite layer. These parameters can be saved and shared later as well. Maybe I settle on a report output or a custom KPI that I want to be able to return to. I can save this set of parameters and share it with my colleagues. There's no barrier to diving deeper here either. It's very easy to visualize the raw source data underneath each of these index layers. Here I am taking a look at flooding risk categories from FEMA, just as one example. We can generate statistics for any of our regions of interest. We can even draw our own polygons in order to capture exactly the area that is relevant to our questions. All of this is how HDOT is boosting climate resilience using cloud-native geospatial analytics, rapid analytical prototyping, parameterized composite scoring, to drive decisions using big geospatial data. Thank you.
Thank you. Next to the stage, we welcome Colonel Mark Reed of the United States Military Academy and his paper, West Point Rain Event.
Okay, keep your seatbelts fastened. Good afternoon. My name is Colonel Mark Reed. I serve as the head of the Department of Geography and Environmental Engineering at West Point. West Point is situated on the Hudson River, about 50 miles north of us here at Columbia University. Each year, 1,000 of our graduates commission with a Bachelor of Science into the United States Army as second lieutenants. This past summer, on July 9th, West Point and the surrounding communities experienced an unprecedented rainfall event. The initial forecast for us was about 1.5 to 2 inches of total rainfall for the day. You can see that indicated here as the forecast map. But the forecasts were very wrong. The frontal system stalled, and a warm, moist air mass surged into the region from the south. Topography, we think, likely enhanced the rain event in our location. In the end, this event dumped over 8 inches of rain in a 6-hour period from 1 p.m. to 7 p.m., bringing a 1,000-year rain event. Our weather station at West Point recorded some truly remarkable numbers. I can show you just a few of those. This graph shows the cumulative rainfall at our weather station from 1 to 7 p.m. on the 9th. Average monthly rainfall in July for our region is about 4 inches. This single 6-hour event, we received nearly 2 months worth of rain in a 6-hour period. 4 months later, we're still recovering from and repairing the damage. Roads remain closed. Damaged homes are yet to be fully repaired, and storm drainage systems remain inoperable. The event also caused significant damage in the surrounding communities. This video was taken by one of my faculty members at his home in nearby Fort Montgomery. We'll take a quick look at some of the damage in the community. Washouts from the flooding event created extensive delays for faculty living off-post. Some main access roads remain closed for weeks, and New York 218 that you see here along the Hudson between West Point and Cornwall remains closed indefinitely. On base, neighborhoods where our staff and faculty reside experienced extensive flooding, mass wasting, and erosion. The volume of debris was truly astonishing. This rugby field is normally covered in turf and is regularly used by cadets and faculty for physical fitness and sporting events. I've never seen debris flows of this scale in the Hudson Highlands. Every morning, I look out my bedroom window at this washout. Our engineers estimate this to be a $9 million repair job. Within days of the flooding event, our department's GIS team began surveying the damage, collecting data, and building a community GIS dashboard. Here you see the largest road washout on West Point. Washington Road is still closed, and our engineers estimate this is a $15 million repair job. We've collected a significant amount of data across the installation using our surveying equipment, terrestrial LiDAR systems, and drones. For the most significantly damaged areas, we built models that we'll be able to analyze and use in the classroom for years to come. Using a combination of drone imagery, LiDAR, and ground surveying stations, our GIS team created 3D models of the massive washout on Washington Road. The resulting video that we'll see here in a second not only captures the physical damage from the event, but also continues to serve as a teaching aid in our remote sensing and surveying classes that we offer to our cadets. Our GIS cadets and faculty also created the storm damage dashboard for our community leaders and post engineers, showing near real-time updates to repair projects across the installation. So far, the total damage estimate is over $200 million just for West Point. Each of the sites on the dashboard includes relevant metadata and photos, which has assisted project managers and the Army Corps of Engineers as they make repairs. This has been both a valuable resource for the community and a great learning opportunity for our cadets. The rain event on the 9th of July exposed West Point's vulnerability to severe or to extreme weather events. The flooding from just 6 hours of rain severely disrupted West Point's mission. Fortunately, no one was hurt. We did have one local killed in the nearby community. We aim to leverage this event as an educating opportunity for our cadets, work with partners to improve installation resilience, raise awareness about changing riskscapes, and offer innovative solutions for our Army and the Department of Defense. And this event, bottom line, fits a pattern of increased extreme rainfall and flooding events in the Northeast, as described in the latest National Climate Assessment Report just out and the IPCC's 6th Assessment Report. In line with the Army's climate strategy, West Point and the Army are committed to enhancing resilience and adapting to current and future climate risks. I'd like to just briefly thank Captains Emily Madison and Court Adams who helped me put this together. Thank you very much.
Thank you, Colonel Reed. John Konarski's statement yesterday that 2050 is here in 2023, we can see it right in our own backyard just upstate. Our final speaker in this series is Mr. Bradley Riley, also of the World Bank, Hot Cities, Cool Heads, Advancing City Responses to Extreme Heat in South Africa.
Good afternoon, everyone. So I'm Bradley Riley from the World Bank's GFDRR, and I'll be presenting a quick snapshot of the work that we are currently doing and also some research that I've done with the University of the Witwatersrand. So as we know, as many of the speakers have highlighted, extreme heat is a current challenge, and it's going to increase in the future, and it's going to be exacerbated with affecting many livelihoods and populations around the world, with specific impacts on the health, food and water security, economy, infrastructure, and labor productivity. So in recent years, increasing deaths and hospitalizations have been linked to extreme heat, particularly during heat waves, and this is mainly in the urban areas and cities, which are at a higher risk than most other areas. So this is due to your urban materials and infrastructure absorbing and radiating the sun's energy. So however, unlike the Western world, this has become poorly recognized within the African continent and specifically South Africa. So our work has begun to try to understand the current heat context in South Africa to try and inform and advance heat responses and heat resilience in the country. So we began by identifying the present and future heat stress, and we did this by mobilizing over 100 community members in a citizen science approach. So they collected heat readings, which was basically modeled to identify the future and current heat stress throughout the city level. Well, firstly at a city level, as you can see here, and this kind of identifies the urban heat intensities at a city scale, and this is the city of Johannesburg. And you can really see, you can simply see the distribution of the urban heat island effect, with some areas actually being above 6 degrees Celsius. We then further went into a meter scale neighborhood analysis to identify the disparities at a local level. So we did this using an historical heat wave days, and then we actually further simulated a heat wave under a high carbon emission scenario where during the 2050 period. So the next we're going to look at is heat vulnerability and who is affected. So we have actually created a heat vulnerability index based on socioeconomic indicators, and this map that you can see here is in the city of Johannesburg. And we have clearly highlighted that there's distribution of vulnerability throughout the city, as we know. And we've selected specific areas of high vulnerability where we want targeted solutions. And you can actually see on the top right, it's an area in Alexandra where there's a high vulnerability there, but there's also, you can see there's so little tree cover compared to on the bottom where there's a lower vulnerability in that area with excessive tree cover. So it really shows the disparities and inequality in greening between the rich and poor. And I really love this image, which kind of shows you the context of this. This is an area in Johannesburg, and you can see on the left-hand side you get these prosperous, really nice green suburbs, and over the road you get these informal settlements with no greening, and this is based on, or in part due to the legacy of apartheid urban planning. So this kind of leads on to the next point of what vegetation and cool buildings actually can do and how it reduces heat stress. So we use some great thermographic imagery and LiDAR and FLIR cameras to actually show this. So on the top right there, you can actually see how shaded versus non-shaded areas actually results in a huge difference. So it's over 10 degrees Celsius less in temperature in the shaded areas than compared to the non-shaded. So what do we do from here? What is the kind of the purpose and heat action that we can actually get from here? So we like to look at heat action in 3 central themes: your places, your people, and your institutions. So your places, there's the environment where the populations and communities live in. So you want to create this urban greening initiatives, so increase your tree canopies and reduce the urban heat island effect. These cooling strategies like this picture here, which is the painting of your white roofs to lower indoor heat exposure. And lastly, your community cool spaces, so areas where people can go and escape from extreme heat, get medical advice, and also get hydration. But also the next aspect is your people. So we need to make sure that the local populations, the communities, are aware and alert of incoming periods of extreme heat and how to respond to that. We need to build capacity of the health workers and the emergency responders on what heat illnesses look like and how to respond to that. And lastly, our protection of our workforce, specifically our physical laborers who are in direct sun exposure and heat exposure during the course of the day, and their interests need to be taken into account. And lastly, our institutions and our governance dynamics. So we need to have a look at the heatwave risk management cycles. So heat needs to be looked at 3 stages: your pre-heat wave, your during heat wave, and your post-heat wave. And ultimately, this will lead into your heat action plan, which is an integrated approach from all the strategies that I've mentioned above into an integrated management approach, which can be mainstreamed across city departments and across a city and a country for effective heat resilience. So thank you so much. I could talk for so much longer, but please have a look at the QR code. And yeah, thanks so much. Bye.
Thank you. Let's give one more hand to all of our presenters.